6665. When operating an aircraft with a constant speed propeller, which procedure places the least stress on cylinder components? A. When power settings are being increased, increase manifold pressure before RPM. B. When power settings are being decreased, reduce manifold pressure before RPM. C. Whether power settings are being increased or decreased, RPM is adjusted before manifold pressure. The correct answer is B. In an aircraft with a constant speed propeller, the pilot has the ability to independently control both manifold pressure and RPM, propeller speed. Manifold pressure represents the power output of the engine, while RPM controls the rotational speed of the propeller. Reducing manifold pressure before RPM during power reductions helps to minimize stress on cylinder components for the following reasons. Combustion pressure. Reducing manifold pressure before RPM decreases the pressure within the cylinders, which reduces the stress on the combustion chamber and cylinder components. The sudden reduction of power without reducing manifold pressure first could result in high-pressure differentials within the cylinders, leading to potential damage or stress on piston rings, cylinder walls, and other internal components. Cylinder cooling. Lowering manifold pressure before RPM helps maintain adequate cylinder cooling. When manifold pressure is reduced first, it decreases the amount of fuel-air mixture being injected into the cylinders. This reduction in mixture flow helps prevent overheating of the cylinders and reduces the likelihood of detonation or pre-ignition, which can lead to cylinder damage. Propeller speed control. By reducing manifold pressure first, the pilot ensures that the propeller is not driving against high power demands while reducing RPM. This reduces the load on the engine and minimizes the stress on the propeller blades, engine mounts, and other associated components. Smooth power reduction. Reducing manifold pressure before RPM allows for a smoother power reduction sequence. By gradually decreasing the manifold pressure, the pilot can better manage the power changes and ensure a controlled and gradual reduction in power, preventing sudden and potentially damaging fluctuations in engine load and stress on cylinder components. 6666. To absorb maximum engine power and to develop maximum thrust, a constant speed propeller should be adjusted to a blade angle, which will produce A. Large angle of attack and low RPM. B. Large angle of attack and high RPM. C. Small angle of attack and high RPM. The correct answer is C. A constant speed propeller is designed to maintain a constant RPM, revolutions per minute, regardless of the aircraft's airspeed. It achieves this by automatically adjusting the blade angle to optimize performance based on the engine power and the desired aircraft speed. To understand why a small angle of attack and high RPM are necessary for maximum power absorption and thrust development, we need to consider the aerodynamic principles at play. Angle of attack. The angle of attack refers to the angle between the chord line of the propeller blade, the straight line connecting the leading and trailing edges, and the oncoming airflow. A larger angle of attack increases the lift generated by the propeller, but also creates more drag. Power absorption. The purpose of adjusting the propeller blade angle is to allow it to absorb the maximum amount of engine power. By setting a small angle of attack, the propeller blades present a smaller resistance to the airflow. This reduces drag and allows the engine to transfer more power to the propeller, resulting in higher efficiency and power absorption. Thrust development. To develop maximum thrust, the propeller needs to efficiently convert engine power into forward thrust. By adjusting the propeller to a small angle of attack, the thrust produced per unit of power input is maximized. This configuration enables the propeller to effectively bite into the air and push the aircraft forward with greater force. High RPM. Additionally, a high RPM setting is required to achieve maximum power absorption and thrust development. The rotational speed of the propeller affects its efficiency and the amount of air it can move per unit of time. Higher RPM allows the propeller to generate more thrust by moving a larger mass of air at a faster rate. In summary, it suggests adjusting the constant speed propeller to a small angle of attack and high RPM is the correct choice for absorbing maximum engine power and developing maximum thrust. This configuration minimizes drag, maximizes power absorption, and optimizes the propeller's ability to convert engine power into forward thrust. 6598. The rotor blade pitch angle is the acute angle between the blade chord line and the A. Angle of attack. B. Rotor plane of rotation. C. Direction of the relative wind. The correct answer is B. The rotor blade pitch angle refers to the angle at which the blades of a rotor are set or tilted in relation to the rotor's plane of rotation. This angle determines the amount of lift generated by the rotor and plays a crucial role in the performance and control of rotorcraft such as helicopters. Here's why the pitch angle is measured with respect to the rotor plane of rotation. Rotor plane of rotation. The rotor plane of rotation is a fixed reference plane defined by the rotational axis of the rotor. It represents the plane in which the rotor blades rotate as the rotor spins. The rotor plane of rotation is perpendicular to the rotor hub axis, and it remains fixed relative to the rotor system. Blade chord line. The chord line of a rotor blade is a straight line that connects the leading edge and the trailing edge of the blade. It is an imaginary line that represents the average shape of the blade cross-section. The chord line is typically straight, although it may have a slight curvature. Pitch angle measurement. The pitch angle is defined as the acute angle between the chord line of the rotor blade and the rotor plane of rotation. This means that the measurement is taken with respect to the fixed reference plane formed by the rotor's rotation. The chord line serves as a reference for determining the pitch angle. By measuring the pitch angle with respect to the rotor plane of rotation, we can accurately describe the tilt or angle at which the rotor blades are set relative to the rotational axis. This angle determines the amount of lift and thrust generated by the rotor and affects the helicopter's performance, stability, and control. 6695. Which statement is true concerning rotor systems? A. The main rotor blades of a semi-rigid rotor system can flap and feather as a unit. B. The horizontal flapping hinge on a fully articulated rotor system enables the main rotor blades to hunt. C. Dampers are normally incorporated in a fully articulated rotor system to prevent excessive motion about the spanwise axis of each rotor blade. The correct answer is A. Rotor systems are critical components of rotary wing aircraft, such as helicopters. They are responsible for generating lift and providing the necessary thrust for flight. Different rotor systems are designed with specific characteristics and mechanisms to achieve optimal performance. The main rotor blades of a semi-rigid rotor system can flap and feather as a unit. In a semi-rigid rotor system, the rotor blades are attached to the rotor hub using a combination of rigid and flexible components. This design allows the rotor blades to flap and feather as a unit. 6696. The main rotor blades of a fully articulated rotor system can A. Flap and feather collectively. B. Flap, drag, and feather independently. C. Flap and drag independently, but can feather collectively only. The correct answer is B. The main rotor blades of a fully articulated rotor system can flap, drag, and feather independently. Flapping. Flapping refers to the up and down motion of the rotor blades as they rotate. In a fully articulated rotor system, each rotor blade is attached to the rotor hub through individual hinges that allow independent flapping. This means that each blade can move up and down relative to the rotor hub, adapting to changes in lift and aerodynamic forces. Dragging, also known as lead lag motion, refers to the back and forth motion of the rotor blades along their spanwise axis. In a fully articulated rotor system, each blade is allowed to move independently in the dragging direction. This flexibility allows the blades to adjust their position and angle to accommodate variations in rotational speed and aerodynamic loads. Feathering. Feathering refers to the individual adjustment of the pitch angle of each rotor blade. In a fully articulated rotor system, each blade can be feathered independently. This capability allows for individual control of the lift produced by each blade, helping to maintain rotor balance and control the helicopter's flight characteristics. By providing independent flapping, dragging, and feathering capabilities to each rotor blade, a fully articulated rotor system offers enhanced control, stability, and performance for the helicopter. This design allows for precise adjustment of each blade's position, pitch, and angle of attack, optimizing the rotor's efficiency and maneuverability.